So to connect with what I was doing last time. Okay, so last time, where was this? Okay, no, something is missing here. So what happened last time? I did some isoperimetric inequality, right? Okay, okay. So the pages have gotten reversed. So this we saw the isoperimetric inequality, right? So there we say that so this we have that in the plane, if you take any curve and the area bounded by the curve for a given area, the perimeter is maximized by by the disk. So for example, so here, so let's just continue a bit about that. So in the circle, in the plane, if omega is a Jordan domain, omega gamma is a domain, okay, is a domain bounded by Jordan curve gamma. We'll assume that it is smooth. Then we saw that area of gamma is bounded by, so what did we show? Area is at most the perimeter squared by square divided by 4 pi. Okay. So in particular, what we get is that the length.
Area of omega.
Oh yeah, sorry. This is area of omega. So the length of the, so in other words, so the length of the boundary divided by the area is greater than equal to something like, so is it 4 pi divided by the length of gamma. Okay, so this is what we get. So this is fine, but if you just look at this ratio, it can be made arbitrarily small because you can actually, so equality is achieved when it's a circle. So if you take gamma to be a circle of radius r, then what is it? So the length of gamma is 2 pi r and area of omega is actually pi r squared, right? So if you look at this ratio, what you get is, I mean, anyway, it is equal to this. So this ratio will be equal to, in this particular case, in this case, it will be equal to 4 pi divided by 2 pi r, which is whatever it is, it's some constant over r, which can be made goes to 0 as r goes to infinity. Okay. So this is true in the plane. So meaning what we are saying is that you can find regions such that the boundary to volume ratio can be made arbitrarily small. Okay. But if there are other situations where this cannot be done, so I will let me mention. So some of you may have seen this, some of you may have not seen this. There is other things like hyperbolic plane. So what is hyperbolic plane? Okay, so let me give very cut and dried quick definition. Hyperbolic plane is basically, it is the unit disk. So this is the unit disk. Okay, with Riemannian metric. I will explain what this means. Okay, for the purpose that we have Riemannian metric. Dx square plus dy square over 1 minus mod z square the whole square. Okay, what does that mean? So where z is x minus z is x plus iy. Okay, so what is the meaning of this? Okay, what is the meaning of this? So there are two things. So this just means that if I have a curve gamma, okay, so let's say gamma of a, gamma of b. Okay, so gamma, suppose is a curve. Smooth curve. Then the length of gamma is defined not with the usual one. So the usual definition would have been we would take integral a to b gamma dot of t and then take the well, it's a vector, so norm of that dt, right? That's what we would do. But now we don't do that. We use this metric. So the length is going to depend on where you are. Okay. So it will, how will it depend? So if you are at location gamma t, then the length is given by this kind of thing. So it will be gamma dot of t divided by 1 minus, not dot. In the bottom, it's not dot, it is 1 minus gamma of t squared dt. Right? So is there a square in the denominator? No, it's just the 1 minus dt. So the point is at each, so if you're at some location z, what does this 1 over 1 minus mod z square the whole square? So nearby, all the lengths have to be expanded by this factor. So if you're closer to the boundary, 1 over 1 minus mod z square is going to be close to infinity. Okay, so the reciprocal, so 1 minus mod z square will be close to 1 and this will blow up. So a small region will have, I mean, any small thing, you have to blow up the length by this factor 1 minus mod z square. So that's what we are doing. So this gamma dot of t would be the usual Euclidean length. You blow it up by this much, or 1 minus this one, and integrate. And also, if I have some region omega, area of omega, so omega is contained in the disk. You can take any measurable set. So area of omega is defined. So this is the definition, is integral over omega. So what we would have done is usually just 1 dx dy. That's what we would integrate to get the Euclidean area. But now we have to weight it by this factor. That's what the Riemannian metric is supposed to do. What you do is you just 1 minus mod z square means x square minus y square. Mod z square is x square plus y square. So you do this. So this is the definition of the area of omega. Okay. So this is an interesting geometry. As defined, it might not make sense. Why on earth would you define it like this, etc.? It comes from some more conceptual basis, but this is the quickest way to define what the hyperbolic plane is. Just take it for now. Okay, so it is a nice place. So what it is actually you would have seen pictures of Escher and so on. So you would have seen. So that well, okay, let me not bother about that now. Or if I have a picture of Escher, then I can show it. That is the quickest way to. So, well, let me see. Can I? I'm just looking up some. Okay, so I have here something. I will just.
You can even copy paste it here if you want it in the notes.
Yeah, so then I'll have to just download. So I'll just maybe that's kind of what I'm doing. So if I
just screenshot, no, you can just take a screenshot. I don't know what the control keys are, but anyway, yeah, that's fine.
Okay. Maybe I can just share the screen itself for a moment. So this is an example of a picture of Escher, which you would have no doubt seen. So this is a depiction of the hyperbolic plane. So you have the unit disk and you have all this fish here. Okay, so the way to think of hyperbolic plane is that you think of each fish as having the same size. Although to your eye it will look that this is smaller than this, but no. You imagine that all the fish have the same size. That tells you the metric. Okay, that tells you the metric. So for example, if I want to go from this point here where I'm pointing, you see the cursor, right? So let's say I want to go from this point to somewhere here on this side. So the point is, if I take a straight curve like this, it's like I'm going through this region where the lengths are expanded a lot. So this one tends to have large length. So a quicker way to get there in terms of minimizing hyperbolic length is to go a little bit inside where the inflation factor of the Euclidean length, that 1 over 1 minus mod z square, is less. So you see this white curve like this, that is the straight line in this geometry. Okay, and these fish are all of the same size. That is how one thinks of hyperbolic plane. Is that okay? I mean, so does that give, I mean, if you have not seen Riemannian geometry, so I thought I'll just explain that point. But anyway, so with that, what one can ask, why did I bring that in? So you can do isoperimetric inequality there. So the thing is, here it turns out to be rather different. One can do an exact isoperimetric inequality. It turns out so for any smooth Jordan curve, so Jordan curve means closed Jordan curve. So you think of a Jordan curve here. Okay, and then omega is here, gamma is the boundary. Okay, gamma with interior omega. Turns out that if you look at the length of gamma as defined here and divide by the area of gamma, it is always bounded below by some constant. I don't remember what the constant is. So for fixed, so for some C positive, there is some universal number. You can never can make it smaller than that. The thing is, the space is very large. So if here the boundary tends to be extremely large. So whatever you do, so for example, this you might say, let me take a circle like this. This also turns out to be a circle in the hyperbolic plane. So if I take a circle centered at the origin here, so if I take this, the length of this, so the area of this also goes to infinity as you do this. So let's say this is r times the disk. So then this turns out, what would this be? So you are integrating from 0 to r, 0 to 2 pi, 1 over 1 minus, if I do it in polar coordinates, 1 minus t square the whole square t dt. That's what the area will be. Whereas the length of the boundary, this is r e to the I theta, right? So you will get 0 to 2 pi. So gamma t is now r e to the I theta. So its derivative is I r e to the I theta. So the modulus is anyway r divided by 1 minus r square. Sorry, I should write 1 minus r square dt, which is actually, it doesn't depend on anything. It is 2 pi r over 1 minus r square. And you calculate this. Okay, this is an easy calculation. So can I quickly do it? It is 2 pi into integral 0 to r t over 1 minus t square the whole square dt. It is just the derivative of 1 over 1 minus t square, right? If I differentiate this, I get the square with 2t. So I get minus pi into this 0 to r, which is something. When t is 0, you get pi into 1 minus 1 over 1 minus r square, which is pi into r square over 1 minus r square. So you see, if you look at the ratio of the two, this is blowing up as r goes to 1. This is blowing up as r goes to 1, but the ratio doesn't blow up. Length by area turns out in this case to be 2 pi r by r 1 minus r square by this, which gives me something like 1 by r, which goes to 1 only. Okay, so it is always greater than equal to 1 in this case. Okay, so we get or maybe I missed a factor of 2 or something, 2 over r or something, whatever it is, some universal constant. So boundary can never be made too small. Okay, so this is the idea of isoperimetric inequality here. Now what we are going into is graphs. So you can do similar thing in graphs. So what is it in graphs? So let's say very quickly. So if you look at an infinite graph like Z2. So if you take an infinite graph like Z2, so for any subset of the vertices, so you define the boundary to be all the edges connecting a vertex in A to a vertex in A complement. Okay, so A is a finite set. So here, what is the, so this is like the boundary. Okay, so what we look at is, if you look at the boundary to volume ratio, volume is the size. This is the cardinality of the set. Boundary is the cardinality of the number of edges. Okay, so for example, if you take something like a square like picture, so let's say you take minus 0 to n, 1 to n squared. So this is 1, 2 up to n squared. Okay, now in this case, the volume, if that is my A, if A is this, then the area is, I mean, area means the size of this is n squared. Whereas the boundary has length, how much? You have these edges which go out, these edges which go out. It is something like 4 times n plus 1 or 4 into n or something like that, 4n maybe, approximately, whatever. So this, by this, you have a lower bound, but that is like in this case is like 1 by n or 4 by n, which goes to 0. So can be made small. So there exist sets with small boundary but large area. That's what this is. Okay. Whereas if you take a different graph like the tree, so this is this Z2 is like the discrete version of Euclidean space that we saw. Okay, like the plane, it's a discretization of the plane. What is like a discretization of the hyperbolic plane? That is actually a tree. So you take a tree with 3 regular tree, for example. So a 3 regular tree looks like this. Here again, you can take any A in the vertex set. So with finite, it turns out that the boundary to volume ratio is always greater than or equal to a constant for some C positive. Okay. Why is that? So it is actually not hard to prove. Suppose the size of A is, let us say, K. Okay, so suppose the size of A is, so you take K vertices. Okay, so what is the size of the boundary of A? Okay, so for the first tile, right, 3K, because for each vertex has 3 neighbors, right? Each vertex has 3 neighbors. So the number of edges coming out of the edges vertices in A is how much? 12. It's 3K minus number of edges connecting within K, within A. Right? Maybe a factor of 2. So what I'm saying is you want to count edges which connect a vertex in A to vertex outside. Well, first let's look at all vertices coming out of A. A has K vertices and each vertex has 3 edges. So 3K is the first term, but you have to subtract all those that connect 2 vertices within A. That is, but that will be subtracted. Yeah, so and you have to subtract it twice, once from this vertex, once from the other vertex. So 2 times the number of edges connecting within A. Now, how many edges are there connecting within A? Okay, so the number, this is a tree. So A being a subset of T as a subgraph. It is a forest. Forest means it's a tree, it's like a tree, but need not be connected. So for example, your A could consist of 2 different things here. Okay, maybe it consists of 3. So then there is only 1 edge coming between these 2. So that's why the number, so this quantity, the number of edges is actually bounded at most. If it was connected, you would have K vertices and a tree will have K minus 1. Okay.
Should it be 3k by 2 minus number of edges, Manjunath?
Okay. Is it 3k by 2? No, it is just 3k.
Because number of edges.
No, but things going outside. So I just counted the number of edges coming out of vertices in A, and I subtract. But those will be, yeah. So no, the which connect to outside, I think you don't need to subtract, right? I mean, that's counted only once.
3k by 2 gives you total number of edges going in or out of A.
Why 3k by 2? I mean,
because k number of vertices.
Yeah.
And
so
3k is the if you double count, you get 3k.
No. Why do you say double count? Suppose A is only a single vertex. So how many edges are coming out of that? 3.
Every
right?
times 3. Yeah, exactly.
Not 3 by 2. If A is a singleton, the number of edges coming out of A is 3. And I don't need to subtract anything. This number will be 0.
Oh, I see. So then it is 3k minus 2 times the whole divided by 2.
No, not really.
No. Oh, okay.
Things that are going out, there is no double counting there. So let us see here. Let's say A consists of 3 vertices. So at first I'm counting 3 plus 3 plus 3. So I counted it as 9. But now I have to subtract this one twice. So I get 7, and that is indeed so 1, 2, 3, 4, 5, 6, 7. That is actually the number of edges going out.
Okay, thanks.
Yeah. So this whole thing is greater than equal to 3k minus 2 times k. So this will be greater than equal to k plus 1. So you see that you get that del A over A cardinality is greater than equal to k plus 1 by k, which is 1. In this case. So this is the analog of the hyperbolic plane. So here isoperimetric inequality, it says that you cannot have a small boundary. Whatever set you take, you cannot decrease the boundary. If you take a large set, the boundary will also have to be large. So that is actually the gist of what we are going to do. What we want to construct are basically finite graphs with this kind of property. Okay. Of course, in finite, what does it mean? I mean, so if you take a finite graph, if you take A to be all the vertices, then you have no boundary and you can make it 0. Or even if you take A to be almost the whole graph, the outside edges will be very small, so you can make it small. So you have to quantify in a proper way. Okay, so that is what we are going to do. So expander graphs are basically graphs with this kind of tree-like property, that they have sets have large boundary. That is what is required. Okay, so that's where we are headed. Any questions, comments so far? Okay, so let's just make some basic definitions. G is VE. So V is a finite set, which we will take to be 1 to up to n. Always n will denote the number of vertices for me. What is E? E is edges. Well, okay, so let me state multiple edges and loops allowed. So what it means is, so I have a vertex set like this. So I have edges between, so let's say vertices are labeled 1, 2, 3, and 4. So maybe 1 and 2, 1 and 3 form an edge, and maybe 2 and 4 form an edge. Maybe between 2 and 3 there are 2 edges. Maybe from 4 there is also a self loop. Okay. So edges are, so it is undirected first of all. Okay, so let me just take a quick poll here. So is there anybody who is not familiar with these terms? I mean, is this clear? All the terms are clear to everyone? That when I say undirected edges, multiple edges, loops, is this clear what they mean? So, I mean, if somebody has not ever seen it, then I can explain. But okay, so it looks like everyone is familiar with it. So this is a graph. Okay, so this is a finite graph for me. So it can have self loops and multiple edges. That's just for convenience. So simple graph would be where you don't allow multiple edges and loops. Okay, so now let's associate to it two matrices. Okay, so some associated matrices, which will be important later. So one is the adjacency matrix. So if I need, I'll write it as AG. It is a n by n matrix. So where the I comma j entry, the entries are Aij, and Aij is 1 if I and j form an edge. Okay, so I and j form an edge is sometimes written like this. If I is adjacent to j, that is Ij is an edge. Okay. 0 if I is not an edge, Ij is not an edge. Okay, so that's the actually more correctly. Okay, if I allow multiple ones, more precisely, Aij is the actually this is okay for simple graphs. That's what you usually think of. But since I said multiple edges allowed, Aij is the number of edges connecting I and j. So that I could be equal to j, in which case it's a loop and it is etc. But otherwise, this is what it is. Okay. So that's what adjacency matrix is, and di degree is just the sum of Aij over j plus number of edges adjacent to vertex I. So di is the sum of Aij. So for example, here this one 1, 2, 3, 4. This has degree 4. This has degree 2. This has 1 and 2. This has degree 2, like this. Okay. So the adjacency matrix here will have, for example, 4 is a loop, so it will have a 1 here, but none of the others is a loop. So the other diagonal entries are 0. And 1 to 2 I have an edge, so I put a 1. 1 to 3 I have an edge, I put 1. And 1 to 4 I don't have an edge, I put 0. 2 to 3 I have 2 edges, so I should put 2 here, etc. Okay, so that's what it is. So then we also have the Laplacian matrix, which we denote L sub g, which is basically it is like this. It's also an n cross n matrix, where on the diagonals we have d1, d2. Actually, yeah. So if I allow loops, then I should do it a bit properly. So let's write it as d minus a. Where d is the diagonal matrix with d1, the degrees on it, and then this is the matrix with Aij entries. Okay, so that's what is called the Laplacian matrix of the graph. Okay, so in other words, so Lij, L of Ij is, well, okay, if G has no loops, so if G is a simple graph, simple graph means no loops, multiple edges, then it is more cleaner to write. It is di if j equal to I, and it is -1 if j is adjacent to I, and 0 otherwise. So that's what it is. On the diagonal you have di's, and on the off diagonal you have -1s. Okay, and let's also define a d-regular graph. Is one with di equal to d for all I in the vertex set. all the degrees are equal to V, okay, equal to D. So in such a case, for such graphs, then the relationship between L and A becomes nicer. It becomes L becomes D times identity minus AG. Because all the degrees are same, it's D times identity minus A, which is nice because what happens is that even spectrum of the two things are related there. Okay, so A is itself a symmetric matrix, by the way. So this is going to be so both A and this is symmetric, and this is also symmetric. These are symmetric matrices, and so the eigenvalues, etc., are very closely related, right? So lambda is an eigenvalue of A if and only if T minus lambda is an eigenvalue of L. Ultimately, we are going to concentrate on d-regular graphs. So this is important. Otherwise, it's not quite related. So whether you want to work in terms of adjacency matrix or in terms of Laplacian matrix may not make actual qualitative difference, but actually you cannot transfer results from one to the other if it's not regular. In the case it's regular, then the eigenvalues will shift. In fact, eigenvectors are going to be the same. Okay, so this is the Laplacian and so on. So one of the things about Laplacian is not just that it is symmetric, but it is positive semi-definite. Okay, so let me make that observation here. If you take LV in a product V, so if V is so okay, L, let's, yeah, V is any vector in Rn. Okay, or let's call U in Rn, which you can think of as a function on vertices. So let's look at LU in a product U. What it will give you is summation di ui square. The quadratic form will give me this times sum over all I adjacent to j. Let's say aij. Let's say yeah. So aij ui uj, where ij and ji are actually repeated. So what we can write is, so we can write over all. Okay, here I am summing over all I and j. Here I am summing over all pairs ij which are edges. Okay, so then what I get is di ui square. No, sorry. So this one you can write quite simply in. So let me just write what you get. You get aij times ui minus uj square. Why? So you just you expand this. You get aij ui square, aij uj square minus 2 aij ui uj. Here you see you have minus 2 aij ui uj, once from ij and once from ji. That is okay. Now aij ui square is there, but when summed over all I, that will give you summed over all j, that will give you di. Okay, so that's the way it comes out. So you get this. So which shows that L is positive semi-definite. And hence eigenvalues are non-negative. But it's actually,
is there a half? Is there a half there, Manju? Because
right. There is a half. You're right. There is a half here. Yeah.
Because the uj squared and ui squared and uj squared, those will contribute same, right? The di.
Right. So, but then minus 2, but I should get 2 aij. Okay. What am I making a mistake here? But here I do get 2 times aij ui uj, right?
Right. So
half or not. So where will, okay, so if we look at ui square, it will come from summation aij and also summation, yeah. So something, what am I making a mistake here? No. Kaushik. So this is being summed over all pairs. Okay, not ordered pairs. Okay, you're summing it over all edges. So if you want to see what comes for UI square comes with the coefficient over all j which are adjacent to I of aij. That's all you get, which is UI square di.
Okay. Oh, so sum here is over all pairs, right?
Yeah, this one
Ij.
is over. Yeah, so this is over all pairs, not over ordered pairs.
Okay.
It's
No,
sum
no. I
over
just.
all. Yeah.
Okay. So if we do the aij uj squared term,
Right.
what do we,
No.
uj square?
No, it doesn't matter. Each UI square will come with all the other edges, all the edges adjacent to it.
Okay. Yeah, got it. Yeah.
So you get aij over, you will get aij or aij, they're the same. So that's what gives you di.
Yeah.
Yeah,
Thanks.
so usually they put a half here, I think, but okay, I haven't put that. But so this is a nice quadratic form. It is positive definite, and you can see it's in fact equal to 0, means L1, L applied to the constant vector is going to be 0. Because if all the UIs are 1, then this is all 0. So this is clear. So this is a positive semi-definite matrix. It is very, very important. It is very closely related. I mean, very much analogous to the usual Laplacian, which we see in continuous, in analysis. So it's very much similar. The usual analysis has a quadratic form which has related to the gradient squared of a function. Laplacian f in a product f is the integral of the gradient square. That is a consequence of Green's theorem. Here it is a more straightforward thing. So, etc. Green's theorem means it's basically integration by parts. Yeah. So we have these things. Okay. So one of the so what is expansion? So let me now introduce the expansion. So let me introduce more terms. Probably I will really get to analyzing them on the next lecture much. But expansion. So H sub G for S and T contained in the vertex set, which are disjoint. No, not necessarily disjoint. Not necessarily disjoint. Let's E of ST be the set of edges with one end in S and other in T. So you could take T equal to S also, in which case you are counting how many edges are there which connect two vertices of S itself. So this is the set of edges. So in particular, if we look at E of S and S complement, is the set of edges with one end in S and the other outside S. So this is like the thing that I was considering in infinite graphs. I was looking at how many edges go from a set to the complement. This is the edge boundary. So this is called the edge boundary of S. These are the edges which are the boundary of S. So I call it edge boundary because there is also a notion of vertex boundary. Vertex boundary is all those vertices which are not in S but adjacent to some element of S. So that could be one, but we will work with edge. Let's stick to this. So when I say boundary, I mean edge boundary. Okay. So then the expansion one. So define H of G. Okay. No, I'll just write H sometimes. So H sub G or H of G. H is a number associated to the graph, which we will define as follows. As the minimum, just like we were doing earlier, you look at any set, see how many edges go out of S and divide by the volume of S, by which we mean just the cardinality of S. Okay, so this, and you want to minimize this over S. This is exactly like what I was doing earlier in trees and Z2, right? I consider a set S and I look at edges going out of S and then divide by the number of elements in S. But in finite graphs, this makes no sense because this minimum will be 0. Okay, but also, even if you don't allow S to be the full set, you can take S to be everything except one vertex. That means what happens? So suppose you take all S to be everything except one vertex, then this will be n minus 1, whereas the number of edges will be just the degree of the vertex you left out. Those are the ones that are, so it can be small. So the correct way to do is you take over all S, but you shouldn't take S to be very large. So you take S less than equal to n by 2. Okay. Yet another way of writing it is you can take min over all S without any condition. You look at edges connecting S and S complement, but you divide by whichever is larger. See, if size of S is at most half of n, size of S complement will be more. So the edges E of SS complement and E of S complement S are the same. So these two are the same thing actually. You can see that, right? So this is the expansion coefficient of a graph. So this is the expansion coefficient of a graph. So this is this measures boundary to volume ratio uniformly. So for all sets basically. So if edge is big, so let's see one example. Maybe I didn't give any example. So let's take an example. If you take something like the complete graph. Then if S is K, okay, if S has K vertices, then E of SS complement is K times n minus K. So therefore, the ratio of the size of the edge boundary to the volume is just n minus K. Okay, so if you do, I mean, so the min, so H, G, so you can take S only up to K less than equal to n by 2, so you get n by 2 here. Okay, or n minus n by 2 or something like that. So it is basically that n by 2, let's write. So that's the expansion, which is very big. This is because every set will have a lot of neighbors. In contrast, if you take G to be, let's say, something like a cycle, discrete cycle. Up to n. So suppose we take a discrete cycle. Now you can take, I mean, even if I take, so if I take S to be 1 to up to n by 2, if I take a contiguous ones, then the number of edges going out is only 2. So what we see is that Hg is at most 2 over n by 2, which is something like 4 over n. It can be made very small. If n is large, this can be very small. Of course, you can make it large by taking a stupid set, like take all the odd vertices, then the H E of SS complement will be n. Okay, so that's not a good way to do it. You want to minimize. You want to take a set which has small boundary, and it makes sense to take a contiguous one. You can show that in fact this is equal actually. So this is what achieves the minimum. It is 4 by n modulo the integer approximation of n by 2. So that's how this measures expansion in graphs. But well, Kn is something that really expands fast, meaning every vertex has a large. So we will see one other way if you want to think expand as something dynamic. what it means is, suppose you start with a vertex, take its neighbors. So in the complete graph, what happens? You start with a vertex and immediately you get everyone. Okay, so it expanded very fast to the whole graph. But in general, even if it is not the whole graph, you expand quickly. The neighborhoods expand quickly, and quickly you cover the whole graph. That's what we will see. So anyway, so what is so maybe I can just so this quantity is the important one. Okay, and let me just, now that we are at it, so let me define an expander graph. It's really an expander graph sequence. Okay, it's a sequence of graphs which can be called expander, not a fixed graph. So Gn called an expander sequence if three things: the number of vertices should go to infinity. We will take vertex set to be n. Sometimes, so we want larger and larger graphs. In other words, sometimes the constructions are such that you may not get every n. Okay, so the construction sometimes that we were going to do, you will not have for every n. Maybe it is only for square n or for prime n and stuff like that. So we just want larger and larger graphs. Then you just want the vertex size to go to infinity. But you also want the degrees to not increase. Okay, so max over I in Vn, degree of I, should be bounded. Should be bounded by some d naught. If there exists d naught finite and it's not positive, such that I want the expansion to be greater than equal to h naught. It should not go to 0. So the expansion coefficient shouldn't go to 0. Main point is you want a sequence of graphs where the expansion doesn't go to 0. But we also want to put that is very easy to achieve. For example, the complete graphs have expansion going up very much. But that is not the point. You want the degrees to be bounded. Here you are allowing large degrees. Okay, so if you put this restriction that the degree, well, that happened simply because you put way too many edges, right? Here, when you bound the number of the degrees, so that means you can put at most, if Vn has size n, if Vn has n vertices, then at most you can put d naught times n edges. Okay, so there is a strong restriction, but still you want to achieve an expansion which doesn't go to 0. The expansion shouldn't go to 0. For example, taking a sequence of cycles it's not an expander because, okay, degrees are bounded, the vertex number of vertices goes to infinity, but n goes to 0. So this second one fails the third condition, the first one fails the second condition. The question is, do such things exist? That's what we are going to construct. That's what we are going to use Fourier analysis to construct. Okay, so we'll come back to that. Yeah, so this h is in terms of this. Okay. Yeah, what did I want to say? Yeah, do you want to say anything further? Yeah, maybe in the few minutes that are remaining. Any questions, comments on this? So this is the main question that we are going to address. So there is a construction due to Margulis. I mean, it's a later construction which we will present using Fourier analysis. That's what uses Fourier analysis.
Sort of connecting back to the start of the class, like, do these expanders eventually, meaning, like, I know you haven't even described them yet, do they connect back to the thing where the length and the area, like in the hyperbolic plane, the length and the area seem to sort of be matched up? And,
so this is, this is already built into the definition. When I say HG shouldn't go to 0, that's exactly what I'm asking. I want
what I mean is, can the discrete Margulis expander be projected back into some geometric object?
No, it is okay. I do not know if that is true actually. So this is a sequence of graphs. I am not sure. Yeah.
Alternately, the hyperbolic geometry kind of suggests that something like this may be possible, and I don't know if that can be discrete.
No, actually, locally, I think this will look just like a tree probably. So what happens is you have a sequence of graphs here. It doesn't have to be for all sequences maybe, but at least if I think what will happen is that if you take your sequence of graphs, so what we will in fact construct is, so we will answer this, yes. So we will use Fourier analysis to construct a sequence of d-regular expanders. Okay, so we will in fact fix a d, it will be d-regular expander. So what will happen is that if you take this Gn, okay, and you take one vertex, so if it's d-regular, say let's say take one vertex, namely vertex 1, and you look at a neighborhood of it, look at everything, all the graphs, the entire graph with all those vertices which are within some distance 100 of it. That entire thing will start looking like a tree. That will look like a irregular tree, in fact. So the loops, there will be loops, but the loops will be the size of the largest, smallest loop will in fact go to infinity and so on. So that is how it will look. So in that sense, this one sense, this graphs will approach a tree. But yeah, so okay. I don't know about the geometric object. They will approach a tree in one sense, yeah. So the point is that's somehow the idea. We want a tree-like thing, but you can't do tree-like thing because then so for example, if I want d-regular, yeah. So hold on. Do I just want this? Yeah. Why can't I take batches? So just patch of a tree. If I take my definition like this, one thing I can take is I can take the first. So what goes wrong if I take this? Maybe. So if I take a regular tree and take
most edges will be inside rather than outside, I think.
No, we take it up to n thing, right? So that is my Gn. So Gn is regular tree up to n generations from one vertex. You start somewhere and take all things within distance n. Now, what can we say? If you take, yeah, I think it will have the expansion property, so there should be no problem. No. Sorry. Okay. So the problem is that I could take. Okay. So what is wrong with this? Why not? I mean, why is this not an example? For example, if you take my set to be all things with the up to first n-1 generations, you see that will be 1 plus 2 plus 2 square plus up to 2 to the n-1. And in the last generation, the boundary will have something like 2 to the n. So they are of the same order. So why is this not a sequence of expanders?
But you have to take only n by 2, right? You can restrict to at most n by 2.
Yeah. So for example, if I take everything up to the n-1 or n-2 generation, that will be about n by 2. Right. So it is
so
one.
So the bottom will be order of n, whereas the number of things will be order n squared, no? Like if you.
No. This is 2 to the n, not n square. So 2 to the n and 2 to the n-1. So the number of things is 1, 3, Okay, 1, 3, and then 3 times 2. 3 times 2 squared, and so on up to 3 times 2 to the n minus 1. These are the generation sizes, okay? So this is a geometric series. So if you add up the first n minus 1 of them, you will get something of the same order as the last term. That's all I meant to say. So if you want to be strict about n by 2, then you may have to stop at n minus 2 or n minus 3.
Yeah,
it doesn't matter, but that is still okay. Yeah. But why is this not an expander?
What if you go from down up? No, that also doesn't help.
Yeah. So
but different branches of the tree, like if you draw it like, yeah.
If you just take all the vertices here, for example, so this is, if I take this to be S, then boundary S is only 1. There's only one edge is coming out of it.
It's 1 o'clock.
Whereas the volume of S is something like the total by 3. Right, so this is very small. The boundary to volume ratio is extremely small. This is not going to work. So we want such things to, so this is why this tree also doesn't work, but that's kind of what we are trying to do. But this tree has this, I mean, this has this full, I mean, there is a finality here. That's the problem. Somehow what you want is somehow to tie it back up so that these things come back, so that you will also have boundary on this side. So that's somehow the idea. Okay, so we will do it.
Can you just go back to the definition, please? I just want to see. So ES. The quantity E of S comma S complement.
That's the number of edges.
Okay.
Connecting a vertex in S to a vertex in S complement.
And then okay, and then mod S is just number of vertices.
Number of vertices, yeah. So this is the number of vertices in.
No, just trying to make sense of this word. This in what way it captures this expansion?
It's exactly boundary to volume ratio.
Boundary of okay, and then I see. Okay.
So for example, so what happens? So if you start with a vertex X, okay. So if you want to think dynamically in terms of expansion, you start with a vertex X, okay, and look at its neighbors. Let's denote it n of X. Okay. So this size will be at least, because X is connected. So if you apply the expansion thing to this, we see that n of X is the number of edges going out of X, right? Sort of, at least that many edges will be there. So n of X by 1 is greater than or equal to H. So this will be at least H.
Right.
Okay. So this is those that are neighbors. So let's say n2 of X is those that are at distance 3, at distance 2.
Mm-hmm.
So you apply it to X union n of X. You take that ball of radius 1 and then apply the expansion coefficient. You will see that this is greater than or equal to H times the size of the ball of radius 1. So in each time, what I mean is ball of radius X R plus 1 minus ball of X radius R is greater than or equal to H times the size of this.
Okay, yeah.
Okay, because you need at least this many edges to get the, I mean, you will have so many edges. Okay, this is vertices and edges, so slight issue, but for a moment, just ignore that issue. So you have so many edges going out of this. Of course, they can meet up actually. So you can't say that they can't meet up. So this is the number of edges that go out of BXR, right? That's what we are saying. At least this many edges go out of BXR. But they can lead to the same edge also. Same vertex outside. So strictly speaking, all you can say is this is greater than or equal to H over D. Because at most D of them can meet. Right?
Yeah, but we are still in a D regular.
Let's say if D is the upper bound for the degree, then you get this. So what you get is V of X R plus 1 is greater than or equal to 1 plus H over D times the ball of radius r. So you see that it's expanding fast, the balls. So it will be like 1 plus h over d to the power r plus 1. So the size of the balls, like in a tree, are expanding exponentially, but only up to the point where the ball of radius r is less than or equal to n by 2. Afterwards, it can't go on expanding like this. Then it will stop, but up to that point, so already you have covered most of the graph, half of the graph.
Yeah. This makes it clear. Yeah, thanks.
So in fact, this one, I was planning to say it later, but from this you can see that if you have such a thing, the diameter of the graph has to be logarithm of the size of the vertex set. It has to be a really small in the sense of diameter. Because you see that in log n number of steps, so how long will you take to reach n by 2? If h is fixed, not going to 0, then in a log n number of steps, you will hit n by 2, right? So from there, you can see that this gn will have diameter at most constant log n, log of vn. So log of the size of the vertex. So these graphs have to be kind of very small in the sense of diameter, for example. It's a small world phenomenon.